Hi, I'm Jorropo. I work for Protocol Labs, and today I want to talk to you about light clients, UnixFS, and other stuff. So the first starting point is, what's a phone? Might seem like a simple question, but many people use phones. This is stats I found online. So we probably, because we're building the new decentralized web, we want people that are using phones to be able to access the decentralized web in a decentralized manner. So, however, this poses technical challenge for us because they have very low RAM, not much CPU. The network is expensive because, like many phone plans, have data caps in place, and you don't want to drain the battery. This is not very compatible with the main implementation I am working on, which is Kubo. It uses lots of RAM. It depends. The CPU, a lot. The network, it runs continuous in the background. And again, the battery will drain fast. So you probably don't want to use Kubo on your phone. And so maybe a thing we can take a look at is what's UnixFS. This is a data format we use to store files on IPFS. Maybe that will give us insights in why Kubo uses so much resources. The first point, which is not actually UnixFS, but that's what is a CID. And it's the key we use to link to files in IPFS. It has multiple fields. The multi-base key tells you how do you decode the data into binary. Then once it's in binary, you can parse it to give us other thing about the CID. The version, which is always one, kinda. The codec is an important thing. We'll see why later. And the hash gives us the algorithm, and the digest, which is the result of the hash. And the hash allows us to do content integrity. So this is the hash of the block this is pointing to. So the most simple kind of codec for us in UnixFS is raw. It's literally simply just some bytes. You hash them, you put the raw codec in front, and you have a valid raw file. Very easy. However, we are limited by the block limits. IPFS will limit us to 2 megabytes per block. So if we have a file that's bigger than this, it won't work. The more complex one, which is where you can do magic, is DAC protobuf. This is a protobuf-based format, and it has many fields. The first one, type. Right now we have a file, but we can also have directories and other stuff. It has some data, which is the start of the it's data that contained in the file. So it's the content, some of the content of the file. And the magic part is a links part, which contains other CIDs we're pointing to. So right now we have 2 CIDs. And so this is concatenating both the data and all the files. So right before we were limited to 2 megabytes per file, but now we can take many of those 2 megabyte files and join them together in bigger files. And because you can also join, you don't have to join raw files, you can also join protobuf files, you can keep joining them together into however big you want. So now we'll just walk through decoding file together to see maybe where is the expense in there. So we start, we have a CID, QMQ. We decode it. We see it has many fields. Version 0, it has a hash. And the codec is DACBB. So let's assume that this is the content of that CID. We decode it. First, we find the data field, which is this. So we found this. Then we look at the links field, which will give us all the file we have to download. So we first download the first of the 2 links. This one is raw, so we don't have protobuf. We directly found the content, and we add it to the file we are reading. We repeat, again, same thing, it's raw file, and now we have the complete sentence, which is kind of boring. But this was extremely easy. in the thing we just did, we just walked what is called a Merkle DAG. So because we have hashes that point to data, that point to other hashes, that's called a Merkle construction. And DAG is in the sense that you can point. It's a graph, basically. We can point to the same file multiple times, and there is no cycle. Because it's cryptographically secure, every time we verify the hash, we also ensure that all of the content is the original content we wanted to download. And because we are able to take very big files and break them into lots of smaller files, we can do parallel download if we want. If we had like a single hash for the complete file, we would need to, every time, we couldn't download it from multiple peers, because you only know if a piece of content is correct once you downloaded the complete block. And if your block is like 20 gigabytes, and you download it from multiple people, you don't know who is cheating and who is not. But because we break down our blocks in lots of small blocks, after 2 megabytes, we always know if the data is correct or not, because it must match the CID we were downloading. But more importantly, what we did was just shuffling a few bytes around, parsing some protobuf, hashing bytes. It's not very expensive. Like, this really shouldn't be expensive. So the chapter 3 is, what if we just did that? So I walk you through how we are decoding files. So I wrote an implementation to just do that. So for that, we start to get into question of like how we actually get the file. So we are going to cheat. This is a list of kind of some stuff that Kubo is doing. We are just not going to do any of that. We are going to use the trustless gateway, which is a thing that was added this year, I think, to the Kubo gateway, that allows us to download a car file and raw blocks. And the key point to this is that because we are downloading the raw UnixFS representation, we can do the process I just walked you on of hashing the block, verifying it, parsing it, and continuing that way. And so my implementation, which I written in Go, in my opinion, it fits all of the requirement as set at the start. It uses very little RAM. The CPU usage it's hash dominated. That means that the thing you spend the most time on is actually hashing the data, which you probably cannot get around because you want to know if your data you downloaded is correct. So that is not really a thing we can work on. The network, because my implementation uses a gateway, it has no background process. It just, when you want to download a file from IPFS, you contact the gateway, it gives you a car file, you parse it, and you're good. And so again, it doesn't run in the background, so it uses very little battery. How we can improve this, maybe? Would be nice to see some medium weight implementation. For example, I think kind of like what Fabrice presented earlier with IRO in mobile. Peer-to-peer is not that expensive. What is expensive is only a few stuff, like helping other people by sending them file. That's expensive because you need to respond to random people that ask you, hey, do you have this? So what if we didn't do that? And the DHT also. The DHT is distributed hash table. That's the way we find files in IPFS. There are other alternatives. One of them is reframe, which is similar to the gateway, but instead of requesting file, you request locations of file. So when you have a reframe server, you can ask it, hey, I would like to know where this file is stored. And a medium weight implementation would be awesome because instead of contacting a gateway that then has to contact the storage providers or a pinning service, you would instead contact a reframe server that will tell you the location of those, and you directly connect, your phone would directly connect to the storage provider or the pinning service. We also want it in other languages. I rate it in Go because it's easy. However, Go is not very easy to use if your project doesn't already use Go. There are big runtime costs and that. So Mark Hazer is working on a Rust implementation, I think. We also want one in C because it's ubiquitous. Ideally, we want to do FFI from Rust, not Zig. And maybe your favorite language. It's surprisingly easy to do. My implementation, 300 lines. it's not quite correct. So in a 1,000 lines of code, you should be done. If you need some help, go on to me. I will be very happy to help you run in Java or whatever. What I did here is, from my experience, I knew how UnixFS worked, how I could make a fast implementation. So I did it. However, it's not very scalable to teach everyone all the time. So I'm also writing some specs, which is part of a global effort on IPFS to make things more standardized and help people that want to implement their own implementation more tailored to their need. If you have links to the code. If you want to see my implementation, it's very alpha. It doesn't really work well. In the UnixFS spec that is still in progress, will be done one day, hopefully. I'm done.